in the Center for Electrical Energy Systems at the University of Hong Kong. And today I'll be talking about refunded emissions payment schemes and also some different types of strategies that we can use to achieve different objectives when implementing these types of schemes. But before jumping into those different strategies, I want to try and break down what a refunded emissions payment scheme is and how it works and the fundamental problem that it's trying to solve. I want to do that using a very simplified model of an electricity market. So here I've got 4 generating technologies. I've got a renewables generator, I've got 2 coal generators, and I've got a gas generator. And along the vertical axis, I've got the short-run marginal cost of production. So how much it costs to produce 1 megawatt hour of energy. And along the horizontal axis, I've got the quantity of energy that is being offered into the market for a given trading interval. So if we put demand into the picture, the market operator's job is to arrange these offers in order of increasing cost. So this is why we have this staircase function here. So this is our merit order of generation. And then dispatch these generators in order of increasing cost up until the point where demand is equal to supply. And then the last committed unit will be setting the price for electricity for the whole market. So in this case, gas would be setting the price for electricity at $41 per megawatt hour. Okay, so what's wrong with the business as usual case? Well, with the exception of renewables, these cheaper technologies are generally bad for the environment. So if we produce 1 megawatt hour of energy using brown coal, we're releasing around 1.6 tons of CO2 into the atmosphere. Okay, so how can we kind of address this environmental economic conflict? Well, one approach is to implement a tax. Okay, so how does a tax reduce emissions? Well, one way it does this is by changing the relative costs of generation. So previously brown coal was cheap, okay, at $10 per megawatt hour, but then under a tax, that brown coal generator needs to pay for the emissions associated with that megawatt hour it's producing. Okay, and we can visualize this. So this is our business as usual case. And then we add in the net liability. So this is the tax that these generators have to pay under a carbon tax. And you can see that the costs for all the fossil fuel units are increasing, but some increase by more than others. So we then rearrange from least cost to most expensive. So we have our merit order of generation, our new merit order of generation. And you can see now that gas has supplanted, so it's moved up the merit order, so it's supplanted coal generators in the merit order. So we're using more gas than we are coal. And even if we have demand at the same level, we have some emissions reduction in this very simplified example. But the problem is that wholesale electricity prices have more than doubled now. Okay, but then the government will say, look, it's fine. We've collected all this tax revenue. Just trust us, okay, to figure out how to spend this. And a refunded emissions payment scheme says, no, we don't really trust the government to spend this money. So instead, we're going to formalize the redistribution of these emissions payments using a rule-based mechanism. So this is a scheme that has been used in Sweden to reduce nitrogen oxide emissions. And the basic way this scheme works is it refunds emissions payments, so tax revenue, in proportion to output. So if we collect Y dollars from all generators over the course of a year, and generator G produces 10% of total energy, then the refund to G is going to be Y multiplied by 10%. Now, in practice, it's a little bit cumbersome to first collect all this money and then give it out again. So what this scheme really boils down to is this, which is shown in this red rectangle, which is the net liability per megawatt hour. So the net penalty or credit is equal to the emissions intensity of a given generator minus the average emissions intensity of the system multiplied by the permit price. Okay, so how does this fit in with our previous example? Well, if we assume the average emissions intensity of the system is 1.01 tons of CO2 per megawatt hour, and the permit price is the same as the carbon tax before, then we can compute these net penalties and credits. Okay, so we can, and if we visualize this, well, we can see that brown coal, because it has an emissions intensity which is above average, is going to be paying a penalty for every megawatt hour it produces, whereas gas and renewables, because they're below this benchmark, they're going to be receiving a credit. Okay, they're rewarded for generating. So then we can construct a new merit order of generation from this. Okay, so aligning these offers in order of increasing cost. and then compared to the business as usual case, and we see that we have exactly the same changes in relative costs as we do with the tax. And as a result, we can have the same merit order effects and the emissions reductions that are associated with that. However, interestingly, wholesale electricity prices have come down. Okay, so it's actually less than the business as usual case. So this is an interesting property of refunded emissions payment schemes in that they can have an indeterminate impact on prices. Prices could go up or down following their introduction, at least in the short run. And the key difference is that the net scheme revenue is zero. So all the money we collected in penalties, we're refunding back to generators in the form of credits. Okay, so before I said that we knew what the average emissions intensity of the system was, but in practice we only know this after energy has been delivered. So at the point in time when a generator is submitting an offer into the market, they don't know what this benchmark value is. So what if we set this benchmark explicitly? Well, what do we get by doing that? Well, we have greater certainty with respect to generator short-run marginal cost because now both the benchmark and the permit price are fixed. Okay, so that's good from a generator's perspective. But from the policymaker's perspective, this scheme is no longer revenue neutral. So I can illustrate this using the previous example. If we now slightly decrease the emissions intensity, and I'm going to call it a baseline now, to 1 tonne of CO2 per megawatt hour, okay, we keep the permit price the same as before. We can go through the same exercise, compute the penalties and the credits, and then rearrange, constructing our new merit order. And compared to the business as usual case, you can see, okay, we have these same merit order effects now. Prices are still slightly less or around the same as the business as usual case, but now we've actually collected more penalties than we've given away in credits. So this scheme is also making money. So it's a very simple stylized example, but it's telling us that if we're careful in the way that we select these parameters, we can achieve different types of objectives with respect to both prices and also scheme revenue targets. Okay, so just to recap, if we fix the permit price in the baseline, we have a greater certainty for generators with respect to their short-run marginal costs, and we're also giving ourselves an additional policy lever. A disadvantage is that we have now uncertain scheme revenue. We're no longer revenue neutral. So in some ways, you can think about risk being transferred from the individual generators onto the policymaker in a similar way that an insurance company would, say, collectivize the risk of individuals. Now, this is the role of the policymaker. So how do we manage these fluctuating scheme revenues? Well, one way to do this would be to periodically update scheme parameters, in particular the emissions intensity baseline. So at a high level, what we'd like is if our scheme revenue is below the target, then we want to decrease the baseline. So in this scenario, we're going to be collecting more penalties than we're giving away in credits. Conversely, if we've got too much money in our bank account, we can be more generous and we can increase the baseline. Now, I don't want to bore you with the derivation of this, but this is a simple updating rule that can accomplish this type of an objective. So I just want to give you the intuition of it though, and basically what it's saying is that for a given calibration interval S, so a calibration interval here I'm defining as the period of time over which these parameters are fixed. Okay, so this is a policy decision. This could be 1 day, 1 week, 1 month. We want to set the baseline such that we anchor it to the expected average emissions intensity of the system over the calibration interval. So this is kind of like the refunded emissions payment scheme previously. But then we increment it or decrement it by an amount which is proportional to our scheme revenue imbalance. So this is kind of like a feedback signal. If we're below our target, this is going to decrease the baseline in the next calibration interval to recover the money that we lost in the previous calibration interval. So we're trying to drive our scheme revenue towards some target value. Okay, and the question is, can we do better than this though? Instead of just looking 1 calibration interval into the future, what if we look several calibration intervals into the future? And this is where model predictive control can come in really handy in the sense that we can forecast the future state of the system, several intervals into the future, and then find the path of baselines that will achieve our revenue target while minimizing changes to the baseline's value, because we like to keep these parameters as steady and predictable as possible. Okay, and then the final step is we implement the first baseline in this path, and then we repeat this every calibration interval. So this is like a standard framework for a model predictive controller. Okay, so this is the program. So I just want to give you the intuition of these different components. The objective function is just trying to penalize deviations in the baseline between successive calibration intervals. And 2 is just imposing a terminal constraint on scheme revenue by saying that the revenue that we start with plus the amount of revenue that we expect to receive over the coming several calibration intervals in the future will equal some final revenue target which we get to specify. And 3 is just ensuring that these baselines are non-negative. Okay, we can add other constraints into this as well. So in order to evaluate these 2 different updating mechanisms, we've used an agent-based simulation approach where we're using a direct current optimal power flow model of the Australian network. So this data set consists of around 900 nodes and over 200 generators. And we have half-hourly demand and renewable energy dispatch data for 2017. We've also performed some scenario reduction on this because we don't want to go through each half hour of the year when running the model. So for each week in 2017, we're identifying 10 representative operating scenarios using a k-means clustering algorithm. And then for each week in the model horizon, we are first, we're fixing the permit price to a constant value. So this doesn't change throughout the model horizon. And we're simply changing the baseline's value to accommodate these fluctuations in scheme revenue. So the way it works is that at the start of each week, we look at our bank account, we see what the revenue imbalance is, we figure out how far away we are from our target. We then input this information into our different updating rules. We compute what the baseline should be for the coming week, and then we run the weekly operating scenarios for that week with the given baseline. Okay, so some more pictures now. In the top figure here, I have the path of baselines from these 2 updating rules, and in the bottom figure, I've got the path of, this is essentially our bank account balance. Okay, so we can see that this single interval rule is really good at hitting the revenue target. So this is the purple curve. And you can think about this as being like a very anxious policymaker. Perhaps they lose $10 this week. Well, that means that next week, they're definitely going to be changing the baseline's value to recover that money that they lost last week. Okay, so that's why we have some more fluctuations in the baseline's path when we're just looking one interval into the future. The MPC rule, though, you can think about this as like a very laid-back policymaker. They lose $10 this week, but that doesn't matter because they know that several weeks into the future there's going to be some change in the state of the system, or they anticipate some change in the system that would recover that money anyway, even if they didn't change the baseline's value. So this is why we have a smoother path of the baseline using the MPC-based rule. However, we have greater fluctuations in scheme revenue. So there's a bit of a trade-off here. Okay, so what else can we do with this? Well, one thing we can do is pursue different types of targets. So because we can control what our scheme revenue target is. So here I've said that from week 10 to week 20, we want to ramp up the amount of money that we have in our bank account. Okay, and we want to see how the baseline responds to this type of a target. And you can see that starting from week 10, we have this divergence from the baseline's value, from the average emissions intensity of the system, which is this orange dashed curve here. So this means that for these weeks, we're collecting more penalties than we're giving away in credits. So we're accumulating money in our bank account. And then once we hit our target, well, these baselines, they just reconverge to this kind of new equilibrium level. Okay, so let's stress test the scheme a little bit. What happens if there's some big shock to generating technologies within the scheme? Maybe some generators come offline. How does the scheme respond to this? Well, here I've got a stylized shock, and I'm saying that at week 10 we have a big reduction in the emissions intensities of existing generators. So perhaps there's some miraculous technology that gets invented and they all implement it at the same time. From the policymaker's perspective, this is great environmentally, but it's also a little bit dangerous because if the baseline doesn't catch up to that new level, well, then the scheme could be running at a deficit. The baseline will be set too high. So the single interval rule, it just cares about the revenue target, so it anticipates what's happening with this shock. So week 10 comes along, it adjusts the baseline accordingly, and we hit the revenue target. The MPC rule is designed to not like abrupt changes in the baseline's value. So prior to the shock occurring, it starts dropping the baseline, so it's accumulating positive scheme revenue. And then when the shock occurs, it draws down on this revenue and then converges to some new equilibrium level. Okay, what happens if the policymakers are sleeping? They don't see this shock coming. Well, in week 10, the baseline's value is set too high, so there's a big deficit in terms of scheme revenue. The single interval rule, so this is the anxious policymaker, they drop the baseline by a lot in week 11 to recover the money they lost in week 10, whereas the MPC rule is dropping the baseline quickly to this new equilibrium level, but then it just sits below it for a period of several weeks until this deficit goes away and then reconverges back to the average emissions intensity of the system. Okay, so to summarize, we've got a short-run revenue rebalancing rule, which is just considering a single period. Revenue is very close to the target, but we have more variation in the baseline's path. And we have an MPC rebalancing rule, which is considering multiple future periods. We have a smoother baseline, but more variation in scheme revenue. Okay, so just to sum up, we've got a carrots and sticks approach to emissions abatement here, where we're internalizing transfers among generators, okay, in a technologically neutral way. We don't care what type of technology we're using, we just care about emissions intensities. And we've got two rule-based updating mechanisms, which are really, at their core, trying to make explicit the parameters that impact generator short-run marginal costs. And I just want to finish the talk on this and just say, by doing this, perhaps we can come up with new ways to hedge risk for potential investors. So in the same way that I can go down to the bank and ask them for a home loan, perhaps they offer me a fixed rate or a variable rate interest rate. Perhaps we can have some similar thinking in terms of policy parameters for emissions abatement schemes like this one here. Okay, thank you.
Thank you, Alexis. Questions? In the back there.
This fluctuation of the policy, because usually the companies that are very affected by these policies, they want stability for their planning, for investments. So you're proposing here a very fluctuating system. How come that? What would be the catch to get them interested in this scheme?
Well, I think under the standard refunded emissions payment type schemes, you have some uncertainty with respect to what the baseline will be. You only know this after energy has been delivered. But for these type of schemes, we're trying to make that cost upfront. So before every trading interval, a generator knows how to adjust their short-run marginal costs in order to accommodate for this type of a policy. Under a traditional refunded emissions payment scheme, it's very difficult to do that. You have to estimate what that policy parameter will be. So yes, there's some fluctuations in terms of the baseline's value, but it does stay within a relatively small range. But at the same time, we're making it explicit. So we're allowing generators to respond to these changes in policy parameters.
Hans.
So I don't know if I got it right. So these revenues you have shown in the last couple of slides, is this revenue again then the redistribution to the different generators like you have shown at the very beginning? So
Yeah. So this is really the imbalance. Okay, so
imbalance, but finally then reallocated again.
yeah, exactly. So it's used as a control signal. So we look at our bank account and we have some target value that we want to hit, and then depending on how far away we are from that target, we figure out how to change the baseline's value such that we get back to that target value.
Okay, great. Let's thank the speaker once more.